Good morning, ladies and gentlemen. Okay, so do this now. A wave has a period of 0.25 cycles per second. What is the frequency? And then, if its speed is 10 meters per second, what is the length of the wave? The wavelength.
So
Okay,
here's our equations.
give it a try.
Pause the video. Do this now.
And we're back. Okay, so you should have something that looks like this. So a wave, if it has a period of that, we're trying to find the frequency. I'm gonna go ahead and use
What's the
this.
symbol for period?
Period is T, capital letter T, right? So I'm gonna go ahead and use this and this, but I'm gonna put T here and frequency on the bottom, like this, right?
Yeah.
And then, actually, a wave has a period. Oh, I
We
lied.
want the frequency.
Miss Moore lied. Don't do like that. Can we keep it just like this? Frequency equals 1 over period. I apologize. We're solving for the frequency, and we're given. I was like, wait, my units up there are cycles per second. So 0.25. Seconds per cycle. Thank you, Mr. Boykin. Okay, so 1 divided by.
Is it gonna be 4?
I think it is. And we get, I put in the wrong. 1 divided by 0.25. It is 4.
4.
4?
What are units of frequency?
Cycles per second.
Cycles per second, also hertz.
Also hertz.
We like cycles per second better, but
Yeah. But you're not wrong if you put hertz.
yeah.
Okay. And then number 2, so we've got our frequency, we've got a period here. If its speed is 10 meters per second,
What's the symbol for wavelength?
what is the length of the wave? Wavelength looks like this.
The Greek letter lambda.
Okay, so you want to know what the wavelength is. Wavelength is right here and right here. Now, we have both period and frequency, right?
Yep.
But we could have calculated the period wrong, so I'm going to use the frequency because it's given in the equation.
No. We were given the period, and we could have calculated the frequency wrong.
What is wrong with me? We're going to go with this one then. I apologize. Jesus. Okay. So we're trying to find the wavelength. I'm going to go ahead and solve this for wavelength. Those
TV.
TV's in the house. So I've got 0.25 seconds per cycle times 10 meters per second. And that's going to give me my wavelength. That is just going to be 2.5.
Yes, ma'am.
Yep. Okay. 2.5. My seconds, they cancel out. Meters per cycle, I'm just going to put meters.
That'll work.
Okay. And how did you do? Hopefully you did good. Okay, I did well. What do these symbols mean? Frequency.
Yep.
That's how fast you're moving your hand, right? Fast
How
or slow.
frequently you're making waves.
Your period. That is your seconds.
The time it takes to make one cycle.
So from boop, boop. Wait, no, sorry.
Yep, that was right.
So from the bottom, boop, boop. Or from
Yep.
the middle, boop, boop.
Yep.
Okay, hopefully that makes sense. I'm like booping around. Okay, wavelength, which is just the if you want to look at it from one crest to another, or one trough to another. Okay,
Yeah.
one wavelength, one cycle, length for one cycle, and then lastly, amplitude, which is how far away from equilibrium you moved your hand,
How big the bump is.
and it's proportional to how much energy is in that wave.
Yes, ma'am.
Okay, so there's a lot of stuff here, but stuff that should be familiar. Miss Moore saw a flash of lightning and heard thunder 3 seconds later. Whoa. Okay, if the speed of sound in air is 343 meters per second, how far away was the lightning?
Lightning be dangerous. It's a good thing to know how far away it is.
Yeah, and I used to live in Indiana, and we had tons of lightning storms. Then I came to California, and they were like, "It's raining outside," and I was like, "This is not rain." But that was years ago. I would say I've lived in California for most of my life at this point.
Yeah.
Okay, so time was 3 seconds,
3 seconds.
and we know the speed.
343 meters per second.
Okay, and we want to figure out how far away it is, right?
Yep. Which equation are we going to use here?
Let's go ahead and go with this one,
I like that.
right? Okay, so I'm just going to go ahead and boy can flip these bad boys. Okay, I'm going to flip them up. I'm going to throw away this pen and grab my new blue one. And let's see here. So I've got, we want the distance, right?
Yes.
Wrong. Okay, times by t on both sides. Okay, and then distance equals speed times time. Our speed is 343 meters per second. Our time, 3 seconds. Okay. Boykin, can you do the human calculator? Does it
It's
strike
going to be
again?
around 1,000.
Strike again. Strike, get it, lightning. Okay. I get 1,029.
1,029 meters. It's about a kilometer away. So,
Cancel.
in 3
yeah.
seconds, sound travels 1 kilometer.
Okay. Next question. Okay, so if the speed of sound is 0.213 miles per second, 0.213 miles per second. Okay, how many miles away was it?
Well, it's going to be the same thing. It's speed times time.
Okay.
The speed is going to be miles per second
This
times
time,
3 seconds.
3 seconds. My units cancel out. I left with miles. So it's just this number times 3. That's a point
3 times
6
6,
2 6. Is that right? No, 629.
639.
639. Oh yeah, you're right. There's a 3 there. 639
639 miles.
miles. Okay, so like a little more than half a mile. Okay.
Yeah, now question here, how much time will it take for the sound to travel 1 mile?
Okay, so if it was 1 mile.
How would we solve the equation for t?
Okay, so if it was 1 mile, let's see, I've got t equals
D over
B,
S.
D over over S or B or whatever.
Yeah.
And you said for 1 mile?
For 1 mile,
1 mile. Okay.
0.213.
And 0.213 seconds.
Seconds, yeah. I said miles.
Okay, so 1 divided by 0.213, and I get 4.7. Let's call it 5. Okay, so about 5. I think my units are a little bit off here. Oh, this is.
Oh, it's
meters,
miles per second.
meters per second, miles per second. I apologize. There we go. I was like, my units are adding up here.
Yeah.
Okay, so about 5 seconds. We got 4.7 there. So what does that mean, Mr. Boykin?
Well, thunders and lightning is dangerous. Lightning can kill you. If lightning is close, you need to take shelter. So when you see the lightning, start counting. 1,001, 1,002, 1,003, 1,004, 1,005. And you hear the thunder, that's 1 mile away.
Thunder!
If it's less than 5 seconds, it's closer than a mile, and it's dangerous.
Okay, so we're saying that 0.2 times 5 is 1 mile. Is 1 mile, right? So this is 1/5 of a mile, 2/5 of a mile, 3/5 of a mile, 4 miles, 5 of a mile. And so if I multiply 0.2 times 5, that's 1 mile. Okay, that's making sense. And after 5 seconds, that's been a mile.
So the speed of sound in air
Yeah.
is a
okay.
very useful thing and can keep you safe.
Let's do some wave behavior.
Those waves had better behave.
Okay, so question for you. Can 2 people be in exactly the same spot at the same time? Do we answer this?
Yeah, go ahead.
So, I know what you're thinking. You've seen those TikTok videos where, like, I don't know if you guys have seen them, where they've got the shadow of themselves and they're in the same spot at the same time. Well, that's TikTok. That's not the real world. So the answer is no. Even if you got someone sitting on your lap, you are not in the exact same spot at the same time.
Somebody gotta move.
So let's go ahead. Let's go ahead and start our pulse lab here. So let me get my handout actually, right here. All right, and here is our Schlinky, and Mr. Boykin's gonna go on this side, and I will go on. Actually, I'll have this on this side, so you don't have to do so many things at once. Okay. So I'm just gonna go ahead and read through the directions. Okay, step 1, clear off the table. Done. A single pulse is sent down the string by starting from equilibrium position, which we're at right now. Snapping the end of the spring in one direction and returning it back to the equilibrium position. Practice sending pulses from both ends. Go ahead, Mr. Boykin. Okay, do that again. Okay, my turn.
Cool.
Okay. So with one partner holding their end so it won't move, the other should send a pulse by snapping their hand to the right. What side does the reflected return?
So you're going to send it down on which side are you going to send it?
I'm going to send it on this side. I'm going to go like this.
All right, so what side does it come back on?
On
Go.
Mr. Boykin's side.
Yeah.
Look at Mr. Boykin's side. Ready? Set. Oh.
Oh, it came back on the opposite side.
Okay. Do you want me to show? No, they can go ahead and rewind it. Okay, repeat
Well,
by snapping. One more time.
Yeah, let's show them again.
Ah.
Here, let me send one. Notice it comes back on the other side.
Okay, so now repeat by snapping to the left. What side does the reflected return? Ah. Oh, sorry, Miss Boykin.
Do it again.
Okay. So,
Cool.
We saw the same thing there. It comes back on the
Opposite side.
Okay. Loop the string through a couple of coils at the end of the spring.
Here, you loop it, I'll hold it.
Bada boom. There you go, sir.
Hold on a second. Give me a second, boys and girls. I got to get this thing. All right.
You good? You good? All right. So now loop the string through a couple of coils at the end of the spring, with one person holding the end of the string instead of the spring, like we have right here. The other should send a pulse by snapping their hand to the right. Okay, so same thing before. I'm going to snap my hand to the right. What side does the pulse come back on? And here.
Whoa. Whoa. I do that again. Goes back on the same side.
That one's hard to see, but it comes back on the same
But you
side.
can see it pretty good in the
Okay, good.
in
Yeah,
this.
pause it, slow motion it, you guys.
Yeah.
Okay, and then I think repeat by sending the pulse to the left. Again, what side does it return? Ah.
Do it again. Goes back on the same side.
Okay. Remove the string. Both partners should send a pulse on the same side of the spring at the same time. What happens when they meet?
Okay, so which side do you want to send it?
Let's do this side here. So Boykin and I are both going to send a pulse to the same side, and we're going to move our hand about the same amount.
Yep.
Ready? 1, 2, 3. Again. 1, 2, 3.
We got a big bump there when they met. Let's do that again. What the heck?
1, 2, 3. Okay, so you guys see that big bump that comes up in the middle there?
Yeah, we sent the pulses on both sides, and when they got to the middle, we got a big bump.
Lastly, okay, both partners should send pulses on opposite sides now. What happens when they meet? So
Which side do you want to? You will do that one, and
Yeah,
I'll send on the
go
other
this way.
side.
Ready? 1, 2, 3.
Oh, I couldn't see that. Do that again.
1, 2, 3.
We did not
see
get a
bump.
big bump.
Okay. So, we good there?
Yeah.
Okay, so what is going on here? Let's talk about what we just seen. Okay, so when a wave reflects from a fixed end, hands that don't move, that's when Mr. Boykin and I were both, Mr. Boykin was holding it.
Yep.
Mr. Boykin's the end that's changing here.
Yeah.
A fixed end, it comes back inverted on the opposite side.
So
Let's
that
go
the
ahead.
term for what we saw when it switched sides was inverted.
And that is important. Okay, so fixed end up here, I'm going to be sending a pulse down. Okay, so predict here. We've got a fixed end. I'm going to send a pulse.
It's going to
What
go
is
on
going
the
to
top.
happen?
Which side will it come back on? Goes down on the top, comes back on the bottom. Down on the top, back on the bottom. That's inverted.
And I'll throw this simulation inside of the thing in the canvas for you. In the canvas. Okay, so
You can play with it.
yeah, so new word. So a fixed end, that's when that end is being held tight. Let me go back over here real quick just to really solidify. So notice there's different options up here. Fixed. This was like Mr. Boykin holding it, and then this was me sending the pulse.
Yeah.
Right? Okay, so just to make sure you guys got that nailed. Okay. And our next definition here. So, did it go? It did not go. Okay, when a wave reflects from a free end, like when we had with the string, our red string, it comes back upright or the same side.
Yeah.
Okay, and this one was, you said it was, you could see it okay on there? So I'm gonna change it to loose end like that. And here we go. So I'm gonna send a pulse on this side. What side will it come back on?
It's free to move. It should come back on the same side. And it does.
Whoa.
Oh. Now it's, so here on this end, it inverts.
Wait, pause, sorry, I messed it up. I accidentally pushed, I pushed a second pulse in there, okay.
Oh, that's okay. And, oh, damping. Goes down the top, comes back on the top. Okay, and then it inverts. This end is free to move, that end is fixed. So at this end we get inversion, it flips over. At this end there's no inversion. So it comes down the top, goes back on the top. Comes down the bottom, goes back on the bottom. Because it's free to move, and that's a very important property of waves. How do waves behave?
How do they be behaving? Or
Oh, you know what we forgot to do?
Huh.
Well, no, let's go ahead and do this.
Good here? Okay.
Yeah.
Okay, so what do I have here? When two traveling waves meet, they interfere. Oh, we forgot to do it.
Yeah, well, no, that's okay.
Okay, when two traveling waves meet, they interfere and pass through each other.
So those the pulses that we were sending towards each other did not bounce off and come back. They pass right on through each other.
Okay, so what does that like actually look like here? So we've got hump A and hump B.
This is where we sent the pulses toward each other on the same side.
Yeah, and what happens is when they finally meet, they add algebraically, like 1 + 1.
Yeah, if
right?
A is +1 and B is +1, A plus B is +2. You got the
Yeah.
bigger bump, and then after they interfere, they
B.
keep right on going through unaffected.
And A keeps going through.
Yep.
Yep. Okay, so we call this constructive interference because you're building something, you're constructing something.
Yeah,
right?
this is a very important idea. Interference in waves produces so many things that we experience here in the world.
Constructive interference. Okay, so how about, what do we have here? Okay.
Well, here's where we sent them on opposite sides.
Right, one on this side and one was on this side.
Yeah.
And well, visually, let's look at what happens. So you can see that when they meet in the middle, where the waves should be, we actually see nothing here. And then it looks like they keep moving through.
So you can say the one on the left is +1 and -1, and +1 plus a -1 is 0. And then they pass right on through each other.
Yeah, and the direction of these arrows is important, right? Because this is like A and B, and then when they meet, A keeps moving through and B keeps moving through.
Yeah.
Right? Okay, now what's going on over here?
Well, the bumps are different sizes.
This one is bigger, this one's a little bit smaller.
So it'd be like +2 and -1.
Yeah, we don't have 0 here. +2 and plus a -1, that gives me a
+1.
okay? And then, so when they meet in the middle, we do still have a little bit of pulse interference here. We get a little bump, but then as they keep moving through, my big +2 bump keeps moving that way, and my -1 bump moves that way.
Right.
Why positive and negative? Well, if this is just an axis, this is up positive, that's down negative.
Yeah, it's simple.
Right?
They add algebraically, and that's what we saw when we were playing with the slinky.
And we call this destructive interference. And again, that's when we send pulses on opposite sides, and it makes a smaller bump or even no bump at all.
Let's go, but what's the next slide?
Next slide has to do with the standing
Let's
wave
play with the slinky again.
Slinky time!
All right, so you hold that steady, and I'm gonna.
Oh!
Now, notice that if I send a pulse, it moves, it goes someplace, it travels from me down to her and back. If I send pulses at exactly the right frequency, notice instead of going back and forth,
It's like they're just standing still.
and those are called
Standing waves! Okay, so standing waves happen when incoming waves interfere with reflected waves at just the right frequency. And Mr. Boykin was sending waves, right?
Yeah.
But he didn't just send one pulse, he was moving his hand at a certain frequency.
Right.
And what happens is the waves that are coming in, whoops, if you send two wave pulses, I'm not going to do a great job of this, but you send another one here, and you see how things get kind of crazy, right? This doesn't look like a standing wave, obviously.
You know what? I'm gonna demonstrate. Here we have a spring that's attached to the flagpole. Oh, you want to do this?
Yeah. Ooh, Mr. Boykin's gonna
Okay.
feature in our film today.
If I send one pulse, 1, 2, 3, 4, 5, 6, 7, 8, 9. One pulse goes back and forth a bunch of times. They're still going back and forth. If I send two pulses, 1, 2, you can see the two pulses in the middle, but on either end, they start to disappear. Why is that? One goes upright, going that way. It inverts and comes back. So what you have is you've got two waves like this. The first one reverts and comes back. They cancel each other out. That's destructive interference. And then they come back. So if I send a bunch of little tiny pulses
Here we go.
at just the right frequency, notice how much I'm moving my hand.
Not very much.
And notice I'm getting big bumps and no bumps. And what's going on? I'm sending a bunch of little pulses that go down on one side and reflect back inverted. And that's called a standing wave. Now, if I don't hit the right frequency,
Oh yeah, let's do this.
if I don't hit the right frequency, well, then I don't have standing waves. You can see
That's
it kind
very
of comes
impressive.
and goes
Yeah.
because I have to hit the right frequency.
Too good, Mr. Boykin.
And I can have, if I send very low frequency,
Just one standing wave.
notice I'm barely moving my hand up and
Yeah.
down. If I go to a higher frequency, and I have to hit just exactly
Oh, this
the
is a good
right-
example. It takes a while, right, for those
They have to go down and back and down and back and add algebraically. So this is one wavelength, 2 bumps. If I go a little bit faster,
see, it takes some time
Nothing.
to calibrate there.
nothing. Got to hit the right frequency. Ha! You get the idea. I give up.
And Boykin, that's a perfect example right there, because Mr. Boykin on that last one, he didn't exactly get it. And you know why is that? It's because the waves that were coming through with constructive and deconstructive interference, they weren't exactly interfering with each other in the right
At the
spots.
right spot. That's exactly right. I couldn't hit the right frequency, so I did not get a standing wave.
So standing waves, it's very obvious when you see one because it looks like there's no wave. It doesn't look like it's moving. It just
Right.
kind of like,
It's just going up and down and up and down.
okay? And it has to do with hitting the right frequency, and that there are waves being sent through, but it has to do with the interference of those waves. So it looks like this, right? And you should draw this in your notebook. What we have here is a couple of wave parts. So we call this the antinode.
The big bump is the
The
antinode.
big bump on both sides. This is the antinode, this is the antinode, antinode, antinode. And then the nodes are right here in this spot.
Yep.
Okay.
That's where equilibrium is.
Yes. And of course I've labeled one wavelength for you from here to here, one wavelength.
Yep.
All right. Are we gonna talk? I don't think
Well-
we're gonna talk anymore about this, do we? Oh, I've got
Isn't there
some-
one last slide?
I've got the words for you guys here. So standing wave parts. So the node, this is where there is destructive interference, no movement, and that makes sense, right? Like everything's being
Crest
canceled
meets
out.
a trough.
Yeah.
Crest going one way meets a trough going the other way, and they cancel each other out. At an antinode, you've got a crest going this way meets a crest coming that way. You get a constructive interference. Here you've got a trough going this way meets a trough going that way, and you get constructive interference.
So here are the words for that. Node is destructive interference. Antinode is constructive interference, a big bump.
Yep.
Okay, and it's pretty straightforward. If you guys were in the classroom, you'd be able to play with it. We did not give them any homework today.
We'll think of something.
We'll think of something and I'll put it on this assignment.
All right.